Chapter 6.2, Laplace transforms of derivatives, integrals, so that ODEs. Okay, so we want to learn, how to solve a differential equation using Laplace transform. Okay, so the derivatives is this: the Laplace transform of the first derivative, okay, first order, is s times Laplace transform of function, original function, minus f of 0. Okay? Without proof, that's what differentiation, derivative is. You multiply, if you have, the one derivative, you multiply 1s to the original function. This is original function Laplace transform, right? Minus, you have to always take out the initial conditions. Okay? You have, if it's a first order, first prime, 1 prime means one initial condition there, right? If you have a double prime, you would have two, initial conditions, right? So you're subtracting the initial conditions. Let's move on to the next order, f double prime. Okay? Then, since it's a 2, you have s squared. Okay? Times Laplace of the original function minus s times f of 0 minus f prime of 0. If it's a second order, we have two initial conditions, right? Two initial conditions. This is velocity. This is displacement. Okay? And this s is, the order of s is, diminishing, like decreasing like that. Okay? And so, if you extend it to nth order, f prime n, okay? Fn prime, then s to the n, right? Because we have the same n power, right? And L of function f minus s to the n minus 1 f of 0 minus Sn minus 2 f prime of 0 blah 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 and f n minus 1 of 0. Okay, that's the full generalization of nth order Laplace transform of derivatives. Okay? Proof? The proof is rather simple. Okay? So all the proof in Laplace transform, you go for the definition and you try to calculate it. So proof. So f of Laplace of f. Plus of f prime is 0 to infinity e to the minus st times f prime of t dt. Okay? That is, this is u and v prime, and integration by parts, e to the minus st f of t from 0 to infinity, right, plus s times 0 to infinity e to the minus st times f dt. Okay? So this is 0 and minus f of 0, right, plus s times L of f. Okay? That's the proof. Laplace transform of integrals. Okay? So Laplace transform of integration from 0 to t f of tau d tau, okay, is 1 over s f of s. Okay? So integral is rather simple. You don't have to worry about initial conditions, right? You just simply, 1 over s. If you have 1 integration, that means 1 over s times. Okay? For proof, you can try it on. So we're going to use this rule or law to solve ODE, right? We can solve ODE for this. Okay? Let me give you an example problem. Y prime minus 2y is e to the 3x. Y of 0 is minus 5. So you take Laplace transform. Whatever is given, you take Laplace bus, right? To go to the S domain. So Laplace transform of y prime minus 2y. Since it's the first time, I'm going to write it very detailed step. Okay? And since the use of linearity of the Laplace transform, you can write this one as this. Minus 2 Laplace of y is Laplace of e to the 3x. Okay? And you learn that the y prime has to be s times, since it's just one first derivative, Laplace of y, and you take out the prime, right, derivative, minus y of 0, right? That's the rule. Okay? All right. And minus 2 Laplace of y, and you go to the Laplace transform table, e to the 3x is 1 over s minus 3. Okay? So you have everything in s domain now. Okay? So this is plus 5. So we can write this one like this. If you want big y, big alphabet is the function in s domain, right? For easier, notation. And this is plus 5, right? Because y of 0 is minus 5. So it's a plus, right? Minus 2 times big Y is 1 over s minus 3. Okay? All right. So you factor this out. S minus 2 is 1 big Y, and minus s minus 3 plus, minus 5. Okay? And this is minus 5s plus 16 divided by s minus 3. So you can calculate the y, the big Y, which is minus 5s plus 16 over s minus 2, s minus 3. Okay? So this is your function, your function in s variables, s domain. Okay, so minus 5s plus 16 over s minus 3, s minus 2. You do this, right? This is the easy one, right? B over s minus 2. And if you solve it, that's a is minus 6, b is 1. Let me skip it. This is an easy case, right? So our y becomes so minus 6 over s minus 2. Sorry. This is s minus 2, s minus 3. This is s minus 2, s minus 3. It doesn't really matter. It just changes the order. Okay? And plus 1 over s minus 3. Okay? And you have to go back to time domain by doing the inverse Laplace transform of big Y. Okay? If you do that, Laplace minus 1 of minus 6 over s minus 2 plus the inverse Laplace. This is also a linear operator, right? So you can write this way. And if you go to the table, okay, s minus something is exponential in time domain, right? So it's easier to find it. So it's minus 6 times e to the 2t plus e to the 3t. Okay, one more example. Y double prime minus 3y prime minus 4y is minus 16t. And we have two initial conditions for the second order system. Y prime of 0 is minus 5. Whenever you see a differential equation, you just simply write accordingly. S square, since it's a second order, you need square times big Y, right? Laplace of Y. And the first initial condition, which is minus 4, you're taking that out. So plus 4 times, since S is second order, you need another, the lower order of S. Okay, so it becomes 4S. And plus, so minus is a plus, right? That's the first term. Whenever you see a terms in differential equation, you simply translate that into Laplace order. Okay, and the second one is 1 prime. Okay, so it means S times Y, and the first initial condition is minus 4, and minus becomes 4. Okay, and the last one is minus 4 times big Y, right? Then the right hand side is, from the table, it is minus 16 over S square. Okay, T is 1 over S square, the table. All right. So now, all you need to do is factor the Y's out. Okay, so S square minus 3S minus 4 times big Y, and you're moving all the terms to the right hand side, right? The numbers. S square minus 4S plus 5 plus 12. So it's 16 over S square minus 4S plus 7. Okay? And you divide this term for the both side. So 1 over 16 over S square minus 4S plus 7 divided by S square minus 3S minus 4. Okay? This one is minus 16. You multiply S square, so every term. Minus 4S cubed, right? Plus 7S square. And S square, if you factor it out, that's what it is. Okay? Right. And partial fraction of this, A over S plus B over S square plus C over S plus 1 plus D over S minus 4. And let me, skip that calculation. A is minus 3, B is 4, C is 1, D is minus 2. Okay? So, the big Y is minus 3 over S plus 4 over S square plus 1 over S plus 1 plus minus 2 over S minus 4. Okay? And, inverse transform of that big Y is, if you go to the table, you can easily find that. So it's minus 3 plus 4t plus e to the minus t minus 2 times e to the 4t. Example 6. Okay? This is kind of shifted problem. Okay, this is an interesting, problem, so we can solve it together. So y double prime plus y is 2t. But the thing is, the initial condition does not start from 0. It starts from pi over 4. Okay? So that is pi over 2. And since it's a second order, we need a velocity, right? Pi over 4, which is 2 minus square root of 2. The problem is, this is, with the Laplace transform, you can easily solve it. The problem is this, right? Initial condition does not start from time 0, but it starts from other than 0. Then everything gets screwed, right? So what we want to do is substitution. This is like that. So, I don't know, arbitrary, function, right? This is time, and this is y. I don't know what y will be. But the thing is, it starts from pi over 4. Okay? That's what it is. The initial condition does not start from 0. It starts from other than 0, pi over 4, this case. Okay? And then, what we do is substitution. We are moving the axis to here. Okay? So we move our axis to there so that it becomes 0 here, right? At this coordinate. This is tilde coordinate, let's say. Okay? All right, like this. So t becomes t tilde plus pi over 4. Okay? So tilde is shifted space. Okay? 0 is shifted. And t is original. Y of t is original. This is t tilde. T tilde. Okay? You're just moving the coordinate by doing that. Alright? So, let's express that in tilde space. Okay? In tilde space, y double prime plus y tilde is 2 times tilde plus pi over 4. Okay? And you are transforming that to the tilde space. Then your y tilde, the initial conditions of tilde, becomes 0. Okay? In tilde space, naturally, the initial condition starts from 0. Okay? Alright. So, and then you solve it. You solve, using the Laplace transform. This is complete, ordinary differential equation in second order, right? And using the Laplace transform, you just solve it. Like s square times y tilde, okay? To express that in the different space, we keep using tilde, and pi over 2 times s minus 2 minus square root of 2 plus y tilde, big Y tilde, is this one, is 2 over s square, right? T tilde is 2 over s square plus pi over 2 over s. Okay? And then you rearrange the solution. So like y tilde becomes 2 over s square plus 1 times s square plus pi over 2 divided by s square plus 1 s plus pi over 2 times s divided by s square plus 1 plus 2 minus square root of 2 s square plus 1. Okay? So are we done? We have to go back to time domain, but it's a time tilde domain, right? It's still time tilde. We are in tilde space still, okay? So if you do that, so y tilde is inverse Laplace transform of big Y tilde. Okay? So it's this 2t tilde plus pi over 2 minus square root of 2 sine t tilde. It becomes, okay? If you go to the table and compare that, that's what it has. And we are not done yet. Although we have y, that's y in tilde space, right? So we have to move it back to original state, time, by doing this. So tau tilde is t minus pi over 4. That's the inverse substitution, right? Okay. So, and if you plug it in and if you calculate it, then finally y is 2t minus sine t plus cosine t. Okay? So if the initial condition does not start from 0, all you do is substitution by the amount of this. That's substitution. Okay? And then solve into the shifted area, shifted space, and then you go back to the original state. Okay?